Today is day 1 on graphing, so do not recycle that paper that we just reviewed over from yesterday's activity. That'll be homework on Friday. Graphing rational functions. Let's get down some important stuff. First off, a rational function is of the form P of x over Q of x, where P of x and Q of x are polynomials. Q of x must have a variable, or an x, but P of x does not necessarily need one. Like all the examples yesterday, there was a constant up top, like a 1 or a 4 or a 3. I don't know all of them, but Q of x definitely needs a variable. So 0, or root, is where the graph intersects the x-axis, also known as an input x value that makes the function 0. You find these by plugging 0 in for y and solving for x. We're going to find the zeros in these following functions. So in our discovery yesterday, we didn't have crazy numerators. I shouldn't say crazy numerators, but we only had constants up top. But if I needed to find the 0, I'm just going to set the equation equal to 0. So I'm going to multiply both sides by 2x plus 8 to get rid of that denominator. When you do this, this side, this left side is being multiplied by 0, so that entire left side becomes 0. And this right side, the 2x plus 8's, undo each other, leaving you with 3x minus 6. We get an x-intercept of 2. So that's the point 2, 0. Let's find the 0 in the next one. So set f of x equal to 0. Multiply both sides by that denominator, x squared minus 1 on both sides. And recognize the left side is going to be 0 since it's being multiplied by 0. And the right side is undone, or the denominator is undone, leaving you with the numerator. Use and multiply add. X plus 9, x minus 2. And negative 9 will be an x-intercept, or a 0. So will positive 2. Vertical asymptote, new word. You saw it yesterday in the activity, but it's going to always be x equals a number. And it's some sort of number that actually makes the function undefined. We're going to find these vertical asymptotes by setting the denominator equal to 0. So let's just go through and find the vertical asymptotes of these functions. Looking at the denominator, because the denominators cannot equal 0. So we counteract that. Well, what if it did equal 0? What is that number? So the vertical asymptote would be negative 3/2. Now we're going to see, okay, so in the activity you had only the answers of integers, but fractions can also be found. I just didn't want that yesterday for easier purposes. Set the denominator only equal to 0. What would make this undefined? The greatest common factor of x and x minus 6. Now we're going to find the two zeros. So one of our zeros is actually the origin. The other 0 is 6. Horizontal asymptotes is, like we saw yesterday, y equals a number. An output y value that the function almost but never reaches as the input x values approaches positive infinity or negative infinity. So as it goes extremely, or I'm going to keep saying the extremes. As the function goes extremely to the right or extremely to the left, it's going to be approaching this number. If the denominator has a higher degree than the my bad. If the denominator has a higher degree than the numerator, then the horizontal asymptote is y equals 0. So if the numerator degree and the denominator degree are actually the same, the horizontal asymptote is equal to the coefficients, the leading coefficient in the top. So if they're the same, y is going to equal the leading coefficient over the leading coefficient, which we haven't really seen yet. However, if the numerator, p of x, has a bigger degree, then there is no horizontal asymptote. We're going to practice finding the horizontal asymptote, looking at degrees, trying to analyze. In the first one, I noticed the degree in the numerator is a 1, degree in the denominator is a 1. So the horizontal asymptote, since they match, when I say match, I mean the degrees. Since the degrees match, the horizontal asymptote is leading coefficient divided by leading coefficient. So degree in the numerator is smaller than the degree in the denominator, or I should keep going back to the language we used in the previous slide. The degree in the denominator is bigger, so automatically horizontal asymptote is y equals 0. Because the denominator power is not higher, because the degrees don't match in the numerator and the denominator, there is no horizontal asymptote. So what we will write is no horizontal asymptote. So let's see how we can use all these pieces, the zeros, the vertical asymptote, the horizontal asymptote, to sort of get an idea of where this hyperbola may exist. Zeros will be the first thing we determine. So that means you set your equation equal to 0 and solve. Left side becomes 0, right side just ends up being the numerator. So we get one nice point on the graph. Let's recall, that's when we zoom in on the denominator. So x minus 4, we need to see what would make that 0, what would make the function undefined. So we're going to draw in a vertical line at 4 on the x-axis. When we do this, it's going to be a dashed line. So when we graph our hyperbola, we'll make sure we start approaching that line and never cross it. Horizontal asymptote, looking at the degrees. Degree in the numerator is 1. Degree in the denominator is 1. So because the degrees match, we're going to have y equals 2 over, that's a leading coefficient of 1. So we're going to draw a horizontal dashed line at y equals 2. So the hyperbola. We're going to do basic hyperbolas, meaning you're going to have the same sort of branches that we had all day yesterday. The branch on the left is going to be close to this horizontal asymptote, go through our x-intercept and approach the vertical asymptote. Close, but never crosses. So sort of a reflection of that, the other branch is going to be up here, won't cross either set of asymptotes. I want you to reread today's lesson. Go back through your notes. What pieces of a rational function help to graph it without an XYT chart, and how? So what are the pieces? What did we use in that last example? How did we use them?